Okay, so we're picking up with example 4, which is going to be a theorem. Um, it's going to be a proof, proving theorem 6.11. And 6.11 basically says that a parallelogram is a rhombus if and only if its diagonals are perpendicular. So we're going to prove that on using, on this proof. And they said do a paragraph proof. Well, we'll just do a two column proof like what we're used to. All right, so we got. Whoops, I need my pencil. Let me get that. Okay, here we go. Statements, reasons. Okay, and so we're going to, take our given. Okay, and we'll put that in there. Okay, we're looking at a rhombus. Okay, A, B, C, D is a rhombus. Okay, and we were, that's given. Oops. All right, and notice that as a rhombus, right, these three congruence marks right here. So all the sides are congruent, okay? All right, well, the other thing that we know is that a rhombus is a parallelogram. Well, what's special about the diagonals of a parallelogram? Well, they bisect each other. So, in other words, this, and I'll use two different congruence marks to make them separate from the sides. So this diagonal is bisected, and in this part, so AX and XC are congruent, and I also know that BX, and I'll do 3 here, is congruent to this, okay, because the diagonals of a parallelogram are bisected, okay, so we know that that's true. So therefore, okay, so then, okay, let's keep going here. I know that AB is congruent to CB. All right. Why do I know this? AB and CB. Because they told us it was a rhombus. What's special about a rhombus? All the sides are congruent. So I can say these two sides are congruent, right? All right. Now the other thing I know, because of the diagonals bisecting, I know, and I just said this, right, was AX is going to be congruent to CX, right? So AX is congruent to CX, okay? This is definition of rhombus. Oops, I should have said that first. And then this one, we would say that they bisect each other, the diagonals bisect each other, maybe a definition of parallelogram, or, because it's a parallelogram. All right, so now what do we got here? We also know that BX right here is congruent to itself, because why? Because of the reflexive property. All right, now notice this. We have basically established that this triangle, ABX right here, ABX, and this triangle, BCX, are congruent to each other, right? Why are they congruent to each other? Because this side's congruent to that side. I got a reflexive side here, and then because of these are the the bisected diagonals, those are also congruent. So I can say that triangle AXB equals triangle CXB. Okay. Why? Because of side, side, side. Okay. Now, because these triangles are congruent, I can say, what can I say about this angle and this angle? I could say that angle AXB is congruent to angle CXB, right? Because corresponding parts of congruent triangles are congruent. So these parts right here are congruent to each other. So CPC, here. All right, now these are congruent and they're a linear pair, right? So I can say that, the measure of this angle AXB plus the measure of angle CXB equals 180, and, the linear definition of linear pair. And, and then I can do the substitution, the measure of angle, AXB plus the measure of angle AXB. Because I said up here that they're congruent, I'm substituting that in, equals 180. And again, so I'm using substitution. So, the paragraph proof doesn't go into all this, but that's basically what they're doing. So 2 times measure of angle AXB, the distributive property again equals 180. And ultimately I can say, well, the measure of angle AXB equals 90. And then I can say the measure of angle CXB, because remember we said they were equal up there, equals 90. And now guess what? We have proven that AC is perpendicular to BD as a result of this, and so by definition of perpendicular. All right, so there you go. There's that proof. Okay, so that's the example 4 proof. All right, now let's let me clear this board, and we're going to do this last example. The last example that I have a diagram for, I guess I should say. Let's pull this in. Here we go. Okay, all right, so now we are looking at example 5, and they're saying, okay, we want you, it says in example 4, paragraph proof was given for theorem 6.11. Write a coordinate proof of the original conditional statement. And it says what? It says given that you have a parallelogram, given that ABCD is a parallelogram, okay, that AC is perpendicular to BD, okay, and we're gonna prove that we have a rhombus. So we're gonna prove that prove that it's a rhombus. Prove that ABCD is a rhombus, okay? All right. The way we're going to do this in this proof, now notice that, and this is a little bit blurry, but so notice that we have this parallelogram, okay? And notice that it's at 0A, this coordinate's at 0A, and then we got B at B0, and then we got C at 0, negative A, and then we got D at negative B0. All right, so we need to prove that we're looking at a rhombus and that we got AC, which is this, is perpendicular to BD, okay? And that's given, that we're told this, okay? And there they are on the axes and everything like that. So we're going to use this general sort of set of coordinates, and we're going to show that we're looking at a rhombus. How are we going to do that? Well, we're going to use the distance formula on these things and show that they're equal. Okay, and we're going to use algebra. All right, so let me erase this a little bit and just to give myself a little bit of space here. I wish I had a bigger eraser than this, but no, it is what it is. All right, so all right, back to the pen. All right, so let's figure out the distance from A to B. Okay. All right, we know it's going to be equal to the square root of. We're going to subtract our x's. All right, so 0 minus b squared plus now our y's, a minus 0 squared. So what is that going to be? Well, that's negative b squared, which is the square root of b squared plus a squared. Okay, and then, we could write them alphabetically, so it's a squared plus b squared. But anyway, it's the same thing, right? All right, now let's do BC. All right, that's going to be, all right, BC. So from here to here, so I'm going to subtract my b's. B minus 0 squared plus 0 minus a minus a squared. So that gives me a plus. Guess what that gives me? Oh, yeah, b squared plus a squared again. All right, let's do CD. I mean, I think you probably know where this is going, but just to complete the example, 0 minus negative b, so that's 0 minus a minus b, and that's squared, plus negative a minus 0 squared. Guess what that's going to equal? This becomes plus b squared plus a squared. How about that? And then last but not least, we're going to do d to a, from here to here. And we're going to end up with negative b minus 0 squared plus 0 minus a squared. And once we do all that, it's all going to shake out to, oops, I'm right here on the edge, b squared plus a squared. So all of these are the same distances. And by virtue of that, then you know you're looking at a rhombus. All right, let me clear this and we're almost done. Last example. Just look in the book with me. It says carpentry. You're building a rectangular frame for a theater set. Okay, I don't know why we need to know that. Okay, and look at the door, or I guess it's a door. Maybe it's not a door. It's a frame. Okay, it's 4 by 6 feet. Okay, it says first you nail 4 pieces of wood together as shown at the right. What is the shape of the frame? So what does that look like? Well, it's a parallelogram, and it's more specifically, it looks like a rectangle, right? Because it's all 90-degree angles, or at least that's what they look like right now. So I'd say it's safe to say that it looks like a rectangle. Okay, let's look at B. It says to make sure the frame is a rectangle, you measure the diagonals. Okay, so here's our door or frame or whatever, and this is 4 feet, and this is 6 feet, and they're saying you got diagonals. Yeah, this is a terrible drawing. All right, and they're saying that one of these is 7 feet, and they're saying the other one is 7 feet 2 inches. And so the question is whether or not you're really looking at a rectangle. Well, what do we know about rectangles and their diagonals? Their diagonals are congruent, right? So if these diagonals are not congruent, something's a little bit slanted somewhere. So that's not a parallelogram. Because if it were, then these would be exactly the same set of inches, maybe 7 inches, 7 feet 1 inch, and so forth. So it's not. Okay, so that is it for now. So I hope you guys are enjoying your day away. And anyway, complete your homework and let me know if you have any questions. Okay, thanks a lot.